Hello, class. This recorded lecture for section 8.1, which deals with the introduction of what we call confidence intervals and statistics. And so let's just jump right into it with some definitions here. And so the idea here is that we're going to take a sample, typically random sample, right? And here it says 100 fourth graders, and we're going to have to run an experiment. And here they're doing a standardized test. And what they're doing is that for these examples in this section, we're going to be given the population standard deviation. Here it's 15. And so after you take those 100 scores, you find that the mean score is 67.30. And say, like, you want to say, what is your confidence level of if you tested another 1,000 kids, that the mean is still going to be 67.30. And if you think about it, the mean of the sample is not going to be exactly the same as the mean of the population. And so that's what this says. And the book actually does a very nice job in describing this, so I would recommend reading it. And so the question that we usually pose is, what do you think the margin of error would be between, say, the mean of our small sample, say 100, and the whole population, say all fourth graders? And we usually give a value, say plus or minus 10. In this case is what we're saying, points wise. And you could see that for the plus or minus 10, we would add 10 to the mean, and that would be the high end. And we subtract 10 from the mean, and that would be the low end. And so how do we deal with this? Well, in statistics, this is where the central limit theorem comes so important, is the idea that if we use the mean as our point estimator, as they call it, the idea that all distributions, given enough samples, resemble a normal distribution with the mean. And here again, with the central limit theorem, as long as you have a value of n greater than 30, I think that's low, but that's what statistics say. Here is our mean, and then our new standard deviation is the population standard deviation divided by the square root of n. And so with that, the idea of confidence interval will take on a very similar calculation as we did in our central limit theorem introduction. So let me introduce a couple more terms for you. The first term is called this critical value. And the idea of this critical value is actually the z-score in this calculation. And that's why I kind of forced you to calculate some z-scores, because I told you would see it again. And so if you remember the idea of our, let me pull up the whiteboard here. I did. Whiteboard is up. So you remember when we talked about our normal distribution, and we said, there's the mean, and then we split them up into standard deviations, right? And when we did that, this was mu plus 1, mean plus 2 standard deviations. Let's see, that was, oops, try that again. And mu plus 3. And we get on the other end, we subtract, right? And so and mu minus 3 standard deviations. So you remember the z-scores? All the z-scores here were 0, 1, 2. and this was 3, and this was -1, -2, -3. And we said approximate it between plus or minus 2 standard deviations was 95%. Well, the exact number is actually real close to that. It's a z-score of 1.96. And exactly between those 2 points, we have a 95% probability that all the points will fall between those 2. And so when we take a look at what we're doing here in this idea of confidence interval, is that we're taking these 2 z-scores, so we're normalizing again with any mean. And here is our area here of 95%, 0.95. So what's in our 2 tails? Again, we talked about that before, but because of the symmetry, we split the last 5% in half, and you have 2% on either side. And so depending on the type of confidence interval, which is that area, right? If it's 90%, it's going to be a different z-score. If it's 99%, it would be a different z-score, et cetera, et cetera. And this book defines margin of error as the z-score, which they call the critical value, times the standard error, which is actually the standard deviation using the central limit theorem. It's standard deviation divided by n. So you can see as n gets bigger, you're dividing by a bigger number, and you can see that margin of error, or the standard error, excuse me, is going to get a little bit smaller. And so here's an example of where we have this mean, standard deviation, and we had 100 fourth graders, right? So if we use a 95% confidence interval, let me pull up here and kind of do it for you, all right? So we had the mean of 67.30 and standard deviation of 15, and n equals 100. So what are we doing here? Well, the first thing we want to do is that standard error. So, and the standard error is defined as the central limit theorem standard deviation. So in this case, that would be 50 divided by square root 100. In this case, that would be 1.5. And if we do a 95% confidence level, that implies that we have a z-score of 1.96. And so when we talk about this margin of error, I'll just call it margin of error. It's the z-score times this. And so in this case, they call this in the book the critical value. The critical value. And in this book, they call this the standard error. I don't know why they don't just call it the z-score and the standard deviation for central limit theorem, but most books do it this way. And so let's do that calculation. So that would be 1.96 times 1.5, and that would be 2.94. So if you think about what this would do, is that for a 95% confidence level, what the little graph would look like here is that, say like we do a little bell curve like that. And so if the mean here is 67.30, and if we add 2.94 to 63.3, you would get 70.24. And so that would be somewhere out here. And so now if we subtract 67.3 minus our standard, or margin of error, excuse me, 2.94, we would get a point down here of 64.36. So this is kind of like the norm.inv calculation where we're trying to find these 2 points. But instead of doing that, we're now doing this confidence level aspect. So here we have a 95% with regards to modeling it as a normal distribution. So reviewing some new terms. The first one is the point estimator, which is going to be the sample mean. The mean is what we're going to be dealing with for many weeks to come. This confidence interval will be given as a percentile or percentage, excuse me, and you'll think about it as the mean is in the center, right? And so the two extremes would be if you have a 90% confidence, you go 40 above or 45 above the mean and 45 below the mean for a 90%, and so on and so forth. And so the confidence level is going to be between 0 and 100%. And that will measure the success rate. And the confidence interval and confidence level is very similar in the sense that we're calculating the area underneath the normal distribution curve. And then the margin of error will give us the 2 points. The margin of error, again, is the z-score times the standard deviation used in the central limit theorem, which will be the population standard deviation divided by the square root of n. And so when you are looking for common confidence levels there, right? And how do we construct the margin of error? We need the z-score, right? And so the z-score common confidence levels are shown right here. And you can get it right out of the table. And so, or you could use your calculator or your spreadsheet to get the z-scores given any one of these types of confidence levels. And so here are the ones that we're going to be using, and this is on slide 12. So this will be handy. You might want to jot that down on a piece of paper or have that slide handy with regards to those calculations. And so here's another example that say like we had a large sample with a mean of 7.1 and a standard error of 2.3. Assuming that n is greater than 30, we could use the central limit theorem idea to provide our confidence level. And so in this case, they're looking for a 90% confidence level. And so what would that look like here? So we have a mean of 7.1 and square root, so our standard error is 2.3. And so our z-score for 90% confidence is 1.645. And so our margin of error, again, is our z-score times our central limit theorem standard deviation. So that would be 1.645 times 2.3, and you would get 3.8. And so what are our 2 extreme points? So the high end you would add, and you would get 10.9. And then the low end you would subtract, and you would get 3.3. And so if we did this, 7.1 is in here. This would be 10.9, and this would be 3.3. And so what do we have here? We have 90% here. And then what are on both sides? Because of the symmetry, we have both these tails would be 5%. And so here's the idea of the z-score. I think of it as z-scores, and they use this alpha over 2 aspect of it, because the way alpha is defined, there it is. So the way alpha is defined is that the 1 minus the alpha is going to be our confidence level. So if our confidence level is 95%, right? 1 minus alpha, if we do this calculation, you bring 95 the other side and alpha over here, you would see alpha equals 5%. And again, when we think about our normal distribution, if this is our confidence level, and so this would be 95%. There's 2.5 on each side, right? And that's where they get the alpha divided by 2, right? Is they split the alpha in half and put it in each one of those little tails that we have indicated right up here in the slide. So I did warn you that the symmetry aspect of the normal distribution really is really important to get a good handle on what's going on with these calculations. So I'm going to stop this recorded lecture. It's starting to get a little long, and I'm going to finish section 8.1 in the next recording.